Hello everyone and welcome. This is the next part of our lovely seminar for mathematical physics. And I'm really happy to see all of you here, that you can guide with such a numbers. And I would like also to introduce Tim Luders, who came to us from the University in Vienna. And he's not alone. He brought a very nice and compelling topic, I guess. So we can look forward for higher dagger structures and their applications. So thanks for coming.
Yeah, thank you for the introduction and thank you for having me. So I don't have a specific end for this talk planned, so we'll just talk until the time runs out and see how far we get. So please ask questions about anything you want to see more about. Many things I will just sketch, but I want to give you sort of an intuition and some motivation for higher dagger structures. And sort of where I want to go in the end is, where my motivation for studying higher dagger structures comes from, is functorial field theories. I will not talk a lot about functorial field theories in this talk. I will be more on the theoretic, theoretic, algebraic side, sort of. But sort of the diagram I'm particularly interested in my research looks something like this. Very sketchy, only in low dimensions I can make this precise. So there is an object which I call n cut G dagger, or G some, let's say, map of topological groups from G to ON. This is an, let's say, n+1 category of n categories with G dagger structures. Then there is a slightly different object, which is the n+1 category of n categories with G Luders structures. There are some nice maps between these, which are adjoined to each other. And there are lots of cross relations of this diagram to other things. So this is related to rigid, symmetric, monoidal n categories, which in turn is somehow related to fully extended topological quantum field theories. And this is somehow related to defect topological quantum field theories. So some of the reason why people are interested in higher dagger structures is because they appear naturally when you study defect TQFTs and fully extended TQFTs. And we'll see some of that in this talk, I hope. But primarily, we will talk about deep dagger structures. Okay, there's not a lot more to be said. So I think I start just with the classical definition of a dagger structure and where it appears in physics, namely the formulation of unitarity in the functorial estimation of quantum field theory. So we'll talk a little bit about that. Let's start with the definition. Very down to earth, very easy. Definition. A dagger category. I think this is the only time that I will actually abbreviate dagger by this symbol, or maybe not. I don't know. Here I didn't do it. Okay, so the dagger category, what is that? It is a category C. Together with it, some structure, namely a dagger structure, which is a functor, which I call dagger, from C to the opposite category. So my category consists of objects and morphisms between these objects, and the opposite category is obtained from the category by reversing the morphisms. That satisfies two properties, namely the composition of the opposite dagger composed with the dagger should be the identity on D, and the dagger should be strictly the identity on objects. That is the definition of a dagger category. Right, so this just means if I go with my dagger structure from C to C off, and then I go with dagger off from C off to C off, which is just C, because if I reverse my morphisms twice, then I just get my original category back. This should be really the identity. And there's no coherence here, it's really a strict identity. Similarly, I really want these objects to be equal, which is a bit strange from a categorical perspective. I will get into that later. That is a dagger category. Let's talk about examples. So we see where these appear in nature. And there are two very nice examples. The first one is the category of Hilbert spaces or Hermitian vector spaces. Let's give it names. Let's call it Perm or Hill. This is really the same settings. So the category I'm considering here is the category of, let's say, Hilbert spaces and something like linear maps. Probably I'm assuming that my Hilbert spaces are finite dimensional for now. The point is that on this category of Hermitian vector spaces or Hilbert spaces, I have this operation. Namely, I have the adjoint operator, which is defined by, let's say, I have such a linear map from some Hilbert space H to some other Hilbert space H prime. Then I define the adjoint operator via the following equation. The inner product in H1 of FH1 and H2 should be the same as the inner product of H1 and F adjoint H2 in H1. This should be the other way around. This is the classical definition of the adjoint operator in the setting of Hilbert spaces, right? And it certainly works for Hermitian vector spaces. So this operation is really identity of objects. I don't do anything with object, and to any map between Hilbert spaces, I can associate this adjoint operator, which really goes in the opposite direction, right? So it goes from H prime to H. And yeah, and the downward adjoint is just my original mapping. Okay, this is one nice example. Another nice example is a bit more geometrically or maybe topologically flavored, namely the category of vortices or co-vortices. So there are many variants of this category or higher category, and I don't want to define it rigorously, but I want to say what how to think about it. So let's say we're considering -1 dimensional manifold. So what is this category? Its objects are d-dimensional closed manifolds, so compact without boundary, and its morphisms are d-dimensional vortices between these d-1 dimensional manifolds. So let's draw some pictures to get some intuition how this category looks like. Let's say there's in the setting of d equals 1, then a closed zero-dimensional manifold is a collection of points. So maybe this could be an object in this category, and this could be an object in this category, and so on. Those are the objects. Well, and there are the morphisms, which are one-dimensional manifolds with boundary connecting such objects. So, for instance, this would be a nice morphism in this category. And it's a category, so it has a composition which is associative and unital. And the composition is essentially given by gluing these things together. In D equals 2, there are some nicer pictures, I would say. So this is something like a joke among topological quantum field theories that you can't give a talk about drawing the pair of pens. So let's do that. There is in D equals 2, we're looking at closed one-dimensional manifolds. So something like loops or several loops, and a typical morphism in here could look something like this. So we could have two loops here and one loop here, and we want a two-dimensional manifold which connects the two of them. And I could take, well, this what is commonly called the pair of pens, because it looks like a pair of pens if you rotate it appropriately. Maybe it's the co-pair of pens, depending on the way of reading things. And again, the composition in this category is given by gluing things together. So for instance, if I have such a thing and I sort of reverse it to get the other way around, and I can glue them together and I get something like something with a hole inside of it. Right. This is a category, and I claim that this here has a dagger structure. And the intuition of this dagger structure is, again, it does nothing with objects by definition. And what it does on morphisms is essentially it reverses them. So for instance, let's draw this as a picture, a pair of pens. If I apply my dagger structure to that, which I write like this, then this could be this morphism. Okay, maybe I can these bracket out they don't have. And at this point. Right. Again, this gives me a dagger structure. You can think of this perhaps in the way that, well, this is a bordism from, if this is an interval of length 2, then I can think of this as, I think I will come to the Q of T, T of T interpretation in just a second, so let's just wait for that, for interpreting the dagger structure in a physical sense. But before we come to field theories that define another thing, namely a dagger functor. Now using a symbol for the dagger again. A dagger functor between two dagger categories, C dagger and C prime dagger prime is a functor. So something like a structure of developing between categories. From C prime. I should write an F here for the functors for F. That satisfies the following property. It should be compatible with the dagger structures. Namely, dagger prime recomposed of F should be the same as F of recomposed with dagger. In fact, dagger categories form a two category. So there's not only dagger categories and morphisms between dagger categories, these dagger functors, there's also higher morphisms between them, which we call dagger natural transformation. So just as the ordinary category of categories is actually a two category, so categories, functors, and natural transformations, dagger categories form a two category. And the two morphisms we call dagger natural transformations, and they're essentially dagger natural transformations, which satisfies another property, namely that its components are isometries. I do not want to define these and give any more details about this to category because we have other things to get to, but in this notation over there, I will call it let's say O1 dagger, or classically in the literature we just call it cut dagger. I'll leave out the one here. So this is really, this object indicates that N is 1 and G is O1 for reasons that will become apparent later. Okay, this was just a remark. Now let's get another definition, or maybe a vague definition. A unitary UFT, in a very broad sense, is a dagger functor from the category of bordisms to the category of lizard spaces, each with the dagger structure specified here. So in Hilt, it's the joint operator, and in bordisms, it's this way of reversing the bordism.
So the only three monoidal?
Yes, yes. Yes, you're definitely right about it. Is a symmetric monoidal. Symmetric monoidal. Yeah, so an ordinary functorial QFT is a symmetric monoidal functor from the symmetric monoidal category of bordisms, where the symmetric monoidal structure is given by the disjoint union of manifolds and bordisms. And the symmetric monoidal structure of Hilbert spaces is given by the tensor product. And the unitary QFT is such a functorial QFT, which is additionally compatible with the dagger structures. So one original motivation for studying these dagger structures and dagger functors is encoding unitarity, or if you're more interested in Euclidean things than reflection positivity, dagger categories and dagger structures are a way of encoding this in this functorial setup. So this is one reason why we care about that. Okay, are there any questions so far?
Yes. Do you ask the dagger functor to be monoidal?
Yes, let's do it. Yeah, I think so. So since these are both symmetric monoidal categories, which have dagger structures, strictly speaking, I would have to define what a symmetric monoidal dagger category is, right? It would be something like a dagger category turned into some symmetric monoidal setting, and this I would really ask to be a symmetric monoidal dagger functor. Yeah.
But I'm not asking for the functor here, so I'm asking for the dagger itself. I mean, should it respect
tender products and
If there are such, yes. Yeah. So here I only define a dagger category, there's no model structure there. So yeah, this is a final definition. But if I want to define what a symmetrical model dagger category is, then I really want it to be compatible with the model structure. Yeah. Integrating definitely. Yeah. Yeah. So this is given in the examples here. For instance, here we have the disjoint union of manifolds and cobordisms, right? And sort of reversing them doesn't interact a lot with the disjoint. So they're naturally compatible with the structure. Yeah. Okay. Yeah, I'm not entirely sure how much to talk about this formalism because I don't want to spend too much time in functorial field theories. So let me just give you a little bit of interpretation what this object over there, which I vaguely defined, does. So first of all, it's a functor from the category of bordisms to the category of field places. And by definition, a functor sends objects to objects and morphisms to morphisms. So an object in this category here is by definition some closed d-1 manifold. And this gets sent under my functor to some element in here, so some Hilbert space. So in physics, that's what would be called the state space of the system. And to any bordism, to such a thing, between two sides closed manifold, I associate some linear map between the associated state spaces. So this is what would be the time evolution, basically. And the requirement that this is unitary basically means that if I reverse the orientation of time in the bordism category, then this is the same as taking the join operator on the Hilbert side. So this is something that really encodes the classical notion of unitarity that you would expect from quantum mechanics. In a way that also makes sense in sort of QFT, well, not just in quantum mechanics. Yeah.
So in the D equal to K, do you get some unitary probability or something?
That's a great question. I'm not sure if unitary TQFTs have been completely classified. So I think there might be something like this. So you basically there's a statement that ordinary closed two-dimensional TQFTs are equivalent to commutative Frobenius algebras, right? Basically because such a functor is completely determined by what it does on circles and very finite number of bordisms. And the additional condition that this functor is a dagger functor could impose some algebraic constraints on this Frobenius algebra. And yeah, I would expect that there is such a notion. I'm surprised I haven't seen this in the literature anywhere, but it seems very natural. Yeah, I would say so. Yeah. Any other questions about that? Okay. Then let's continue with what's going on this side here. So we have defined what dagger categories are, or what the two categories of dagger categories are, roughly. And now we will define what the two category of O1 evolutive categories is. So the idea here is basically that dagger categories are a bit odd from a categorical perspective. Namely, they ask for a strict identity of functors, where you should really ask for a natural transformation, and for strict equality of objects, which is something very unnatural from a categorical perspective. In particular, you cannot transport dagger structures and categories along equivalence of categories. So if you have one dagger category, which is as a category equivalent to another category, then you will not automatically get a dagger structure on that thing, which is a bit strange. And the following notion, so some people call that E-trigger. The following notion sort of makes this problem. You know what the switch means. Let's just stick with that. And O1 evolutive category and a one evolutive category here is the category C. Together with the functor. So it starts out the same way as the dagger category starts out. Together with functor. Let's call it D from C to C. Sorry. Slightly down here. And now there's more data. Oh, this is functor. That's and a natural isomorphism. That's called eta. That goes from the composition of the op with the to the identity of the C, such that a coherence condition is satisfied. Namely, what this does is basically it trivializes the square of D, and if I have basically the threefold power of D, so I consider triples of D, and consider the two ways of trivializing two entries, namely, let's say, via the identity on D composed with eta, or eta composed with the identity on D, suitably modified because the ops. So I'm going to put a slight op -1 here, don't mind that. So these two ways of trivializing the double dual in this triple product should be the same. So this is a very natural coherence condition which you can write out in components. So it would be something like d of eta h should be eta of dA, and then probably -1, probably. Right. So yeah, is visible again. So and the one related category is a category together with this functor D and with natural isomorphism, which trivializes the square of the functor, and this should be coherent in a sense. Okay, what does that have to do with dagger categories? Before I say that, let me just remark that these guys do form a two category. One, right, I'm going to put it. We'll need to categories form a two category. So between them, there is one evolutive functors and one evolutive natural transformations, which is essentially what you would guess if you had to write out appropriate models. So one evolutive functor would be something like a functor between the underlying categories, together with a natural transformation, natural isomorphism, which relates for the functor with this functor D, and then some coherence condition with respect to this eta. And similarly, for one evolutive natural isomorphisms are natural isomorphisms with some coherence condition. So these form the two category. Let's call it cut or one bottle. So these have appeared in the literature before. So maybe say 20 years ago, some people were talking about something like volutive or involutive or anti-involutive categories, and sometimes they meant something like this, up to taking opposites and minor details. So this is also sometimes called anti-involutive. The notation for one volutive because it fits nicer into the naming scheme for the dagger and the categories, but not all fine. Okay.
Yeah. Say what is O1? So what would be ON, let's say?
Or is it? That's a great question, and I will come to that.
Okay.
I will come to that right after. Actually, now is as good. So the statement is, and I hope I get the categorical level right. There is an O1 action. Let's write it properly. There is one action on the 2-1 category of categories defined by, okay, so what I described here is an O1 action on a 2-1 category. So in particular, it's essentially some kind of functor, and to specify this functor, I have to specify what I do with the non-trivial object in C2. And where do I send the non-trivial object in C2? I send it to the opposite functor from cut 1 to cut 1. This is already sufficient. Let's see. Okay, so we want to define one action on the 2-1 category of categories. So I said where I send my non-trivial generator to, namely the opposite functor, so it takes a category and sends it to the opposite category that I can derive. For any category, I can associate the opposite category that's also a category. To each functor, I associate the opposite functor. So any functor between two categories introduces a functor, and so the opposite functor between the two opposite categories. And finally, I send the natural transformation to its opposite to the -1. So here's a little detail in here because taking the opposite functor is really contrary to homomorphism level on the whole two category of categories. That's why I have to restrict to the one category of categories in order for this to actually be a functor here. We need this inversion at this point. But never mind that small detail. What I can now check is that taking off twice. Let's write it like this. Is the identity. Yeah, this is true. So if I take the opposite category twice, I get my original category back. And so this really defines an O1 Z2 action on the two one category of categories. Okay, what does that have to do with this stuff? Let me give you a second definition.
Maybe can you explain what the caps to ones?
Yes. Sorry. So there is a two category of categories, functors, and network transformations, right? And this is really a two category. So there are non-invertible one morphisms and non-invertible two morphisms. And cut to one is the two category of categories, functors, and only the invertible natural transformations. So the natural isomorphism. So what it basically means is everything after level 1 is invertible.
I see. You need this because otherwise the +1 wouldn't.
Exactly.
Okay.
Exactly. Yeah, there's some more subtle thing going on, but I don't think I will get to that today. So maybe you can talk about that later. Right. So let me give you a new definition of O1 rooted categories. And O1 rooted category. Is a homotopy fixed point with respect to the O1 action above. Let's give it a name. So let's call it rho. Okay. Let's unpack the statement a bit. So we know how classical fixed points work, right? So if I have some group acting on something, then I can ask for the objects on which the whole group acts trivially, right? So in the higher categorical world, which we're in here, I wouldn't ask for the two objects to be equal. I would only ask them to be isomorphic, right? So this is where the homotopy part comes in. Namely, what a homotopy fixed point with respect to this an ON action is essentially consists of a map between the identity on C, which is really just C, and the opposite applied to C, which is really just C off. This is a bit unnecessary to write it like this, but how we can think about this is essentially as categories together with a trivialization of the structure given here. So I really want isomorphism between a category and its opposite. This is the first piece of data. And this is precisely what this functor D is over here. And the next piece of data would be something, right, because it's an O1 action on a two category, there's higher covariances, and I want, so the part of the fact that this is the natural isomorphism between the square of D and the identity is really a consequence of this Z2 part here, right? If this was a Z action, then I wouldn't need this part. Does that make sense? Roughly. Another way of saying that this is a homotopy fixed point is this is a functor from the from what? This is a functor from O1 into the pre-category of two categories, which then okay, let's write it down properly. Okay. Action of a, let's say, discrete group for now. I can also talk about topological groups. Actually, let's talk about topological groups. Topological group on the 2 category. Let's call it B, let's call it group G, is a read functor from the delooping of the second fundamental group of G into the free category of 2 categories, sends a single object to my category B. Right, this is just a definition. So let's see how this setup is contained here. So I have the discrete group C2 acting on the 2 category up to 1. So this is by definition a free functor from the grouping of the second fundamental group of G. So what is this object? It has precisely one object. This is what the B is for. And it has, as its one morphisms, the elements of G, and as the higher morphisms sort of paths in G. In the discrete case, we don't have to worry about paths, everything is very simple. And I send a single object to my category B, on which I want my 2 category B, on which I want to act, and then I have to specify this higher coherence data. And if I really properly write such a free functor down, then I can define what homotopy fixed points with respect to this action are. Namely, it's the limit of this free functor. Or another way of phrasing that, which is maybe more down below. Homotopy fixed points with respect to, let's call it again, objects in the 2 category of natural transformations from a constant functor, which sends everything to the trivial 2 category, to the trivial object in here, sorry, to my free functor here. Right. So this is the limit of rho. You can actually compute that. Okay, this was maybe a bit technical, but it's nice that we have defined what an action of topological group on a higher category is, because what's going on over there is we have defined one dilutive categories, and I've told you that they form a 2 category. And from this perspective, it's also clear that they form a 2 category because natural isomorphisms between free functors form a 2 category. The objects are natural isomorphisms, free functors. The one morphisms are how do you call it, modifications, and 2 morphisms are conjugations. So yeah, there's a lot of higher categorical yoga involved here, but the upshot of the whole thing is n cut G ball is really the n+1 category of homotopy fixed points with respect to a G action on the n+1 category of n categories of points, or really the 1 category of n categories. Okay, to pause a bit.
So there is a choice of each functor we take.
Yes. Yeah, that's a very good point. So where does the functor come from? Where does this functor come from? Why do we consider this for one action and not any other, right? Yeah, here's the conjecture. I think I would want to keep this and erase the rest. So let's talk about this again now. Let's say, let's start this vector. The conjecture is the following: the automorphism group of the 1 category of n categories with the joints is isomorphic to ON. And so the subpart of that is that the automorphism group of categories, of the category of categories, so 1 category to is isomorphic to ON. This is a proven statement, this is a conjecture. This is what's called in the literature part of the unicity theorem. So it's a proven theorem that the automorphism group of n categories without the adjoint part is essentially consisting of Z2 factors. So there are these opposite functors. On categories, there's only one opposite functor. There's only one way I can reverse morphisms, but in higher categories, there are several opposite functors. So I can not just reverse the one morphism, I can reverse the two morphisms and three morphisms, I combine them, and so on. So the automorphism group of n cut is really a bunch of Z2s, but the automorphism group of n categories of adjoints is conjecturally ON. This is a conjecture motivated by what is called the stratified cobordism hypothesis. And in a very lax way, it can be phrased as there is a graphical calculus for n categories with adjoints. So the interpretation of this ON action is that if I have this graphical calculus, then I can rotate sort of the framing of my graphical calculus by ON. This is very closely related to the classical cobordism hypothesis, which tells us something about the relation of fully extended TQFTs and rigid symmetrical model n categories. Namely, it says something like there is a canonical ON action on the maximal subgroup point of any rigid symmetrical model n category. Yeah, which is known in some low dimension special cases.
And sorry,
Yes.
conjecture is stated as isomorphism to a strict group, or which kind of group stands on the
Yeah.
line?
Yeah, let's phrase that properly. So so this guy here is in one category. In principle, you would expect it to be an n category. There it gets a bit n plus one category. There it gets a bit subtle again, but it's really meant in the same sense as over here, where I mean by one category, every morphism after level one is invertible. So this is something natural in the infinity setting. In the lower dimension setting, it's a bit unnatural, I guess. But roughly, you can think about this as one category. And in one category, you can look at the automorphisms, right? And this is really a group or an actual group. And this should be an isomorphism of groups. But this is not a most general statement you can make. There's more to be said here.
And when you say category with adjoints, you mean as more visually dagger, or what does it mean to be n cats with adjoints?
Okay. So in an n category, I have n levels of morphisms, right? And for each level of morphisms, I can ask there to be adjoints. So let's define what adjoints in categories are. A two category with adjoints, because in one category there is no adjoint. So we have to find out two categories. There's also sort of the reason why there's no adjoint here. In the two category. B such that for every one morphism, let's call it X from some object A to some object B, there is another, there is a morphism which I can denote by either X dagger, that's common in the literature, or I can denote by R, say, let's call them right adjoints here, and also version of left adjoints. It's a one morphism with two morphisms of evaluation and co-evaluation. From X pre-composed with R to the identity on B and co-evaluation from identity on A to X are composed with X that satisfy the following properties. So you can graphically denote this guy's evaluation as something that looks like this. It goes from X and X right adjoint to the identity. You can denote this graphically by something like this, which goes from the identity at the bottom to X, R, and X. And the condition that these two satisfy is something that is called solver rule or zigzag rule, which is a statement that these two things should be equalities in the two models. So this is what it means for a two category to have right adjoints. Similarly, there's a notion of left adjoints. And if you have a higher category, an n category, then you can ask for such a thing on all levels. So what I mean by n categories of adjoints here is really an n category which has all possible adjoints. So right adjoint and left adjoints on all levels. Okay.
So maybe just a big question. So in your general definition, so if you so you're saying that if the group is ON, if G is ON, then this is what this is meant by the definition. You take this action.
Yeah.
And if you have a different group, then you need an embedding into ON.
Yeah, exactly. So I take my map from G into ON, and then I pull back the sort of ON, so the canonical ON action on interface of joints. This I pull back along this map, right? And again, I can make it precise in very low dimensions for very specific groups, which I plan to do. Yeah, so that's a good point to talk about SO2, dagger, and evolutive categories. Can someone remind me of the time, because I feel like I don't know how much time.
It's about 50 minutes.
Okay, perfect. Okay, so let's talk about an intuitive special case. There was an archive name, so it is what it is. Okay, let's see. So SO2 naturally embeds into O2, right? There's X. SO2. I want to say what an O2 dagger category and an O2 evolutive two categories. Actually, I also want to talk about this, but I'll do this afterwards from me. Okay, let's define what an SO2 dagger two category is. What is that? It is a two category B with right adjoints. Having a joint is a problem, by the way. It's not structure. It looks like structure here because for every so in principle I specify for each one morphism sort of the right adjoint and the separation and co-evaluation data, but there's sort of a contractible space of such choices. So every two choices will be equivalent in the appropriate sense. And an invertible transformation. So a transformation between two functors, which is invertible, it's called S, from the identity to the double adjoint functor with its identity component being with one of the components being strictly identity. Okay, this is a definition. Why is it a good definition and why do we care for it? So two categories of right adjoints I have explained here. So for every one morphism, I have the choice of right adjoint and these evaluation and co-evaluation morphisms. Then I claim that this data gives rise to what's called an adjunction two-functor or double adjoint two-functor, double adjunction two-functor. How do I define this? It sends an object A to itself. It sends a one morphism X to its chosen right adjoint, and it sends a morphism F to. Luckily, I've introduced this sort of graphical titles. What I can do is something like this, up to some minor things. So if I have some two morphism from X to Y, then the right adjoint I define as this here, which goes from Y right adjoint to I started using the dagger. This here I define as the right adjoint of F. Actually, that's the right adjoint, but no. Define the right adjoint. This is a functor from B to B with the one and two morphism first. And so doing that twice, I will just get the functor from B to B. And I could compare this functor to the identity functor on B. And if I compare it with such a two transformation, which consists by definition of one morphisms and two morphisms, which relate these two structures, I can ask for its homomorphisms to be strictly the identity, because this functor is also strictly the identity. In the literature, this is also called a pivotal two category. And maybe if I have a different color, I can really quickly write down what the evolutive version of that is. It's quite simple. I just don't ask for this condition. So while the dagger category, if you remember that the dagger category was something that is strict on some level, so there's strictly the identity of objects. In the SO2 case, it's similar. There's some strict equality of one morphisms, which looks a bit artificial, and then there's the evolutive world where you have something more coherent. And this too is something like a homotopy fixed point with respect to the SO2 action on the free category of two categories, which is a fourth factor. So lots of categorical details involved, but basically to specify this functor, I only have to look at the homotopy groups of SO2, and in particular, I have to look at the first homotopy group of SO2, which is C, while phi0 and phi2 are trivial. So the vague motivation is in order to specify an SO2 action on the lowest level, on the low levels, I only have to specify where I send my generator, and I send the generator somehow to the double adjoint functor. And then you have the simplification of SO2 doing things in terms of homotopy fixed points, namely something like two categories together with a trivialization of that kind of thing. So trivialization of that kind of action, roughly. Okay, these kind of pivotal two categories, or SO2 dagger two categories, synonyms have appeared in the literature, let's say 15 years ago, so in the context of defect TFTs. Right, so the idea is basically that, well, I drew you a Borgism at the beginning, something like a pair of hands, right? Get others going on again. Let's do it again. Let's say I have my Borgism, my pair of hands. Then, so while an ordinary functorial field theory is something that assigns such a thing to some other bright data, like a whole space or time evolution or whatever, a Borgism with defects is additionally allowed to have some stratification. So something like a decomposition into, let's say, line defects, which in the SO2 case, or in the oriented case, can come with an orientation, and well, there might be some other line defect here, which also comes with a line of orientation, and there might be some point defects here, on line defects. And the idea is sort of that I can encode the data of these pictures where sort of the two-dimensional parts of my organism I label with some theories. It's called A, B, and C, and I label my line defects with X and Y, and my point defects with Y and psi. Then the idea is that I can encode the data of the defects, the stratification, in this kind of SO2 dagger 2 category. So the idea is that the object of this 2 category are the sort of the theories governing the two-dimensional parts of my defect, or the higher dimension, the n-dimensional parts. The morphisms are the line defects, here X and Y, and the two morphisms are the point defects, which I can all interpret as morphisms in a higher category. And in particular, I have something like a composition with it, that I can fuse line defects together or something like that. So this is some vague idea that comes from physics. So the point that I want to make is relating this to SO2 dagger 2 categories is that if my 2 category comes from such an object, then it additionally has right joints. Namely, I can reverse the orientation of my line defects. So this is now a line defect which goes in a different direction. And if I reverse the orientation of my line defect twice, I do nothing. This is encoded in the fact that I have this trivialization of the double adjoint. So this is sort of the first kind of higher dagger structures people have considered, and well, back in the days it wasn't known that these are actually dagger structures, so that they fit in sort of this homotopy fixed point regime. But yeah, so this was a very, very brief motivation where they come from in the context of defect activities. So I quickly want to talk about these two parts. Namely, there is a way of going from the dagger world to the polluted world and vice versa. So let's, I don't know, probably I raised everything already about that. So if you remember the definition of a dagger category, it was a category together with some identity objects function, which strictly squares the identity. Then you can interpret that trivially as an O1 polluted category simply by taking this to be the dagger and forgetting that's the identity of objects, and taking this also to be the identity. So any dagger category is very naturally also an O1 polluted category. This is basically what defines this guy in the case of 1 and O1. And similarly, if I just forget this condition here, then I can interpret my SO2 dagger thing as an SO2 polluted structure. So there's not a lot going on in this arrow. Everything that's interesting is happening in this arrow. And what this arrow is essentially doing is it starts out with something polluted, and then it constructs. So I start out with let's say a G polluted 2 category, and I construct a new 2 category on which sort of the lowest level of my polluted structure trivializes. And on this thing, I can construct dagger structure. That takes a while to make precise, and it's easiest in the dagger case. So maybe I do it in the dagger case.
Now, can you reconstruct this identity which you omit on the right hand side? The quality is limited, yes.
Yes. Right. So okay, actually let's do it in this case. You only can currently written a bit more, so it's actually a good idea to do that. So it works pretty much the same way in the dagger case and the SO2 polluted case, which is sort of nice if you're seeing this for the first time. So let's say we have some SO2 polluted categories. So again, this is a 2 category with right adjoints together with this invertible transformation from the identity to the double adjoint, which in the polluted case is not required to have identity components. Then I construct a new category. Construct. Let's call it P prime. Okay, I want to define the 2 categories, so I have to say what are its objects, morphisms, 2 morphisms, and its objects I take to be pairs of an object A and B, and a 2 morphism lambda A from the component of my invertible 2 transformation S, FE, I, to the identity on I. And it's one morphisms and 2 morphisms, I do nothing. I take the same 1 and 2 morphisms as in my 2 category. So what I've done is essentially I look at a new 2 category in which by construction the components, so the lowest components of my transformation trivialize, and then define an SO2 dagger structure on V. Right. So what I have to do, I have to trivialize the double adjoint while having identity components. So what I can do is I start with some 1 morphism X. Then I use my lambda A, say. I don't know if this is the right convention. What I can do is I take the identity on X, so this 2 morphism, and compose it with lambda I, lambda H to minus 1. I get this X to compose with SA. Then I use the component of my invertible 2 transformation S, this is the second piece of data I always have, and get this SB precomposed with the double right adjoint. So this is just the definition of an SO2 polluted structure. It's a transformation from the identity to the double adjoint. And then again, I trivialize this with my chosen lambda. And this here is a nice 2 isomorphism from X to X double right adjoint, because, well, these are invertible by assumption, and this is also invertible in any 2 transformation. So what I've done is I started with an SO2 polluted 2 category, and I constructed a new SO2 dagger 2 category by basically asking for one of these components to be the identity. And then I actually construct this SO2 dagger structure. And in principle, you should
incorrect question, incorrect question. What should I imagine on L lambda A? It is X.
Okay, so these are isomorphisms. And a morphism X from two objects, let's call them A lambda A to B lambda B, is really just one morphism X from A to B in B. So this is something that looks perhaps a bit strange, but I really take the same one morphisms and two morphisms as in my category B. Right, so I don't ask for any compatibility between lambda A and lambda B whatsoever. You can do that. It looks a bit strange, but it has purpose. Okay. Right. The story is pretty much the same in their case. So there you ask sort of for a trivialization of this functor D, which we saw earlier in the definition of the one dilutive category, and trivialize that, and sort of on the new category I construct consisting of objects and trivializations of this D, I get my dagger structure. Pretty much the same story. Okay, this is sort of the other way of going from dilutive things to dagger things. We have seen that in the SO2 n equals 2 case. So I think if I have time, the last thing I want to explain is how.
So lambda is like maps of trivializations, not transitions. Not transition maps.
No, really just trivialization. Yeah, so I'm a bit short on examples in this talk, but so in this paper we wrote, we looked at, let's say, 3 or 4 examples for such SO2 dilutive or SO2 dagger 2 categories. So for instance, there's a physical theory called lambda Wheatbrook theory, and we can encode it in the functorial setting by specifying something like a symmetric monoidal rigid 2 category. And on this, I can construct an SO2 dilutive structure and extract the underlying SO2 dagger structure by really looking at these objects. And well, there is some explicit computations in the paper, so I can talk more about that later, but in which paper? It's called Orbifolds, High Dagger Structures and Idempotence. It's from 2 or 3 months ago. I can write down the archive later on. Right. Right, we want examples, right? We want examples of dagger categories and SO2 dagger 2 categories, and maybe a bit more motivation why we had to bother with this thing in the first place. So what is the advantage of having this? And my argument for that would be, among other things, that any rigid symmetric monoidal N category carries a canonical G dilutive structure conjecture, proven in low dimensions for specific groups. So let's look at this in the simplest case I can imagine, the O1 case. Because yeah, the other cases, so the SO2 case is proven, the spin 2 case is proven, and the O2 case is proven, but they all require a bit more work to write down. This is also in the paper. Maybe I get to that later, but I won't presume I will. Okay, plane. Any rigid, which means it has duals, symmetric monoidal, means there's something like a tensor product, which is somehow derivative in appropriate categorical sense. Category C carries a, I'm over time, so we'll stop after this. O1 evolution. So if you remember, in the one evolution is something that consists of a functor from C to C off. What is this functor? It sends each object to its dual, and then it sends each morphism between the associated morphisms between the duals. So this is really the same construction as here. Any monoidal category of duals I can interpret as a 2 category with adjoints. And then this is really exactly the same construction. So I take as the underlying functor of my O1 evolutive structure the dualization functor, and I take the trivialization of the double dual, which is induced by the symmetric grading. So there's a general fact that in every symmetric monoidal category, whenever I have right adjoints, I have left adjoints, left duals, sorry. And they're canonically isomorphic. From this fact follows that the double dual trivializes in any symmetric monoidal category. which has rules. And one can check that this satisfies the previous condition of the point power of duals. Yeah, there's a lot more to be said on the details here, but so in the SO2 case we saw over there, there's something that's called the Serre automorphism, which is known in the context of fully extended two-dimensional oriented theories. So say there would be something like an any-symmetric model to get the festivals and the joints. There's a canonical solution, it's the Serre automorphism. But I don't want to go too much over time, so let me just stop at this point, I would say.
Great, thank you very much.
Thank you.
So is the time for your questions, remarks?
Please.
In the B pi 2 of G, does this whole thing remember the group structure on G, or does it only remember the score?
Let me restart. To remember the group structure.
So this G is still a group? Is G is still a group or is this group or what?
Here we talk about the group. I'm wondering whether this is automatic from this definition. So let's think about this for a second.
If it will be a finite group, then you can have different groups that have the same number of elements, and so the same.
Right. Yeah, that's definitely correct. Yeah. It's automatic. How do I construct the fundamental group? So by definition, the fundamental group consists of the objects of G, and then I consider paths in G, and I can compose paths, right? And then I consider homotopy between paths, and I can compose these in various ways. And so I have the composition of paths, and I have the group multiplication. And now I'm wondering whether there is some topology argument that tells me whenever I have two compatible sort of multiplications, then they're the same. I'm not sure at the moment. I think this is in there, but right, there's some argument that the higher homotopy groups of some topological groups are abelian, I think, because
Yes,
yeah, there's some argument.
and B of an abelian group is a group like this, right? For an abelian group, B of
Right, exactly. Yeah.
yeah, B of an abelian is abelian. So
Yeah.
there is a model for B which makes it.
Yeah, that's true. Exactly right. Thank you. So right. So I cannot. So for any abelian group, I can take sort of a grouping which gives me a true group, and there are the two sort of the monoidal structure of the true group, and the composition must be the same by something like an Ekman-Hilton argument. Yeah, exactly.
Yes.
So in the non-abelian case, this doesn't work. So so this definition also works in the non-abelian case. And I have to figure out why it is. Yeah, I think it's something along the lines, but we can talk about the details. Yeah.
There is some higher version of looping the looping adjunction. It applies also to groupoids in some sense, but it's more involved
Right.
when it comes to groupoids.
Right. Yes, please.
Maybe I can ask for your last claim. So let's say morally I can think of rigid monoidal categories as representation categories of Hopf algebra. So Tonic Lane says
Right.
basically true. And for the Hopf algebra I have an antipode that is kind of an operation from objects to opposites. Yeah. So is the antipode somehow involved in this business here?
That's a great question. And then follow up. Let's see what could be a true statement. So here I really need the symmetric monoidal structure for this construction. And in general, if I take the representation category of a Hopf algebra, this is not symmetric, right? So there's definitely some discrepancy here. But if I take the it's another question whether if I have Hop algebra and take the representation category, which is monoidal, does it have a natural something like a one evolution or a dagger structure induced by the antipole? Right? Yeah, that's a great question. I don't know. Yeah, that would be nice to have as an example.
It's also true that you have a lot of groups in the background here. So a natural guess would be that the hop algebra is just a group algebra of these groups.
Oh. Yeah, I'm not sure how this precisely relates. But while we're at the point of this specific example, I can maybe tell you briefly that a nice example of emergent monoidal category is the category of vector spaces, right? So it naturally carries in a one solution, and by this construction, I can get a dagger category from that, and the result will be essentially vector spaces that carry something like a non-degenerate symmetric parent. If you would slightly modify this one structure by also incorporating some complex conjugation, then you will actually end up with Hermitian vector spaces. So Hermitian vector spaces here are really the image of vector spaces together with the one solution given by realization and complex conjugation under this functor here. It's nice to have vectors. But yeah. Sorry, any other questions?
Sorry, about the previous question about Hopf algebras, there's just a comment that one can use the antipode to define a dual representation for a, so if you have a finite dimensional representation of a Hopf algebra, then its dual will be a representation. This is what distinguishes Hopf algebras from bialgebras. So this allows you, this should make the category of modules of a Hopf algebra into a finite dimensional modules of Hopf algebra into a rigid category. But I don't think there is a distinguished dagger structure. Like if one takes a trivial Hopf algebra such that its modules are just vector spaces, then yeah, there is no distinguished.
Right. Maybe this is auxiliary structure. So if you have some nice extra structure on your Hopf algebra, then you might get a nice extra structure on the representation category, but I don't know how to make it precise. But yeah, thank you for that.
Probably to take a full category of self-rule representations, and then probably the conceptual will lead to that.
Right. Yeah. So in principle, I don't have to go through the symmetric monoidal approach, right? So in any
this sum is very obvious. From conclusions of power.
Oh, okay. Yeah, that sounds promising. Yeah. Yeah. Yeah, I mean, self-duality is basically what sort of what you get. So if you have something like self-duality or coherent self-duality, that's sort of how this thing works out in the O1 case, right? We didn't talk about it explicitly, but if you consider something like coherently self-dual objects, then you get a dagger structure on that. So I guess in this case it would be this iteration, right? Yeah, good. Sounds good. Right.
Also, that you don't have normal topology on the left-hand side. It's maybe a disadvantage. Or the isomorphism of OM. Yeah? So you can transplant the topology from OM to the automorphism, or I mean, pull back to.
Right.
Yeah, you know the nature topology.
It's a great question. Right. So this has a topology. Right. And the question is this what kind of isomorphism is this? It's not just an isomorphism of groups, but so I guess the proper formulation of this whole thing would be infinity categorical. And in the infinity categorical setting, I would guess that this is also a topological group because it's sort of the it's sort of baked into the infinity categorical setting, right? Like an infinity category is something like a category up to homotopy, right? So I guess in this setting, it would be natural to expect that this is an actual topological group isomorphism. Yeah. Yeah, I think so. But yeah, this is still open conjecture. So the certified combinatorial markov is having to improve.
I think very safe is to consider discrete topology.
Yes. Yeah. Yeah, this works out usually much better. There we can actually prove something. Yeah.
what's your approach to proving this conjecture? More specifically, asking, do you have simple shell sets as a model or simple shell sets or?
Yeah, usually I think people in this working in this field talk about complete single spaces for the most time, but yeah, I think any nice model of n categories would hopefully do. I don't know which one is easiest to work with. So this is really a consequence of right. So there's the ordinary modeling hypothesis, which tells you something like functors from the n category of organisms to some n category are completely classified by the fully reliable object in the n category, basically, right? And the stratified probabilism hypothesis tells you additionally something about if this is if you have a defect TFT, so a functor from the category of defect probabilisms to this n category, can I also classify that in terms of purely algebraic data in my target n category? And to the best of my knowledge, the precise statement of this conjecture is not even clear because it's not easy to define the n category of defect organisms for arbitrary tangential structure. So really the structures you want to compare have to be defined first, and it's still open problem.
Yeah. And to have a fully infinite or unlike approach to categories, you can enrich by some n-1 groupoids your home sets and then compute everything on the n category level.
Right.
So, but there are plenty of problems even defining internal home in such.
Exactly. There's a lot of higher categorical algebra involved there.
Yeah.
And books from Lurie are like 1,000 pages long and more. So yeah, there's a lot of technical detail involved there. So I know at least of some group who's currently working on writing down the n category of defect bordisms in terms of I think as a complete single space. To the best of my knowledge, it should be done in a year or two or so. So yeah, this is very active research. Yeah. So people have kind of figured out that in low-dimensional category theory it will be impossible to define what the n category of organisms is because there's just too much covariance involved. So you have to go to the infinity world sort of. Yes. So very active topic of research. Yeah.
Okay. So any other question? Not okay. Yanchi, do you have any question? No. So thank you very much.
Thank you. Yeah, I mean, there's so much more to be said, but yeah.
Thank you for taking part.